Hello, very good evening to all of you. From my end, I'm recording it in the evening time. So myself, Ankit Kargeti. I'm a PhD scholar at BML MUNJAL University, and so I'll be talking on this your theoretical calculations, basically the corner calculations on molecules with the donor-π-acceptor structures for the organic field effect transistors. So let me start this. Yeah. So the content of my slides are introduction about the your organic semiconducting materials and the organic field effect transistors, and then about your motivation and the objectives, research methodology, and results. Then conclusion, of course. So if you see the introductory slide, so here I have shown the schematic diagram of organic field effect transistors, where you have a semiconducting layer that is basically your, maybe it could be your N channel or it can be your P channel, similar to the inorganic transistors which we deal with daily basis. So we have a source and drain here. So basically this can be your kind of a NPN structure, where you have a P-type channel, or you can have a PNP type of your structure. So then you will have your N-type channel. So it is one way of your sort of your fabrication of the transistor, and the other way is that where you have a source and drain electrodes on the bottom side. So this is your bottom approach of designing, and it is your top kind of top approach, or top to bottom approach. So these are the schematic of your organic field effect transistors. And if I come to this your this picture graphical representation of the progress of organic field effects, then you will see that mobility of these your charge carriers in the organic field effect transistors is not so high in comparison to the inorganic your system or silicon based your FETs. So if you see, this is the graph which I've taken from the Professor Hasegawa Hasegawa's paper on the organic field effect transistors using single crystals. And I would just give you one I'd like to note that Professor Hasegawa has also had a talk in our symposium, so we had a chance to meet him. So that was just in connection with that. So this, if you see this black, your rectangular positions are basically representing your the polycrystalline organic field effect transistor. So it can be of your rubbery, tetrosine, pentosine kind of crystals. So their mobility is almost around the amorphous silicon in comparison to that. And that's not so high. It's about your below 10, right? 10 centimeters square per volt per second. So if you look at this single crystalline or organic field effect transistor, so this is basically in the region of below 100, and it could be your similar to the polycrystalline silicon. Of course, it is very less in comparison to the single crystals of the silicon or single crystalline materials of the inorganic based systems. Therefore, a number of papers of the research is happening in the field of organic semiconducting materials to design some sort of new molecules which could have the high mobility charge carriers. It could be of your holes, or it could be of your electrons. We know that it is one type of charge carrier is the basis for transference of your current in the your field effect transistors. So this field started basically If you look up the whole history of this organic semiconductor materials, it's a 100-year-old history. And once in 1906, I think, when anthracene crystal was supposed to get this the proper charge injected into them, so it could pass the charges. So from there, it started that organic materials can be utilized for this sort of your charge transference, or this could be utilizable in the form of your current, right, to get to pass on the current through that. So transistor basically it started in, I think, around 1950s, when we first got this your silicon based transistor developed at Bell Labs by the, I think, Muhammad Atala and gang, some other researchers. But the whole organic systems came into the picture after the 1986. So if I say the 1986 was the time when first 19 I think that was Mitsubishi company was working in this electronic materials, designing that. So this your polythiophene. Polythiophene was the material first they grown up. They single the sort of your they could pass on. They could use this polythiophene layer for this transference of the charges. So that was sort of your basic p-type. It's a majority charge carriers for the whole, so it was a p-type your system. And since then it has been a huge progress. So let me just go to this next slide of mine. My motivation is that we want just the alternation of the or the substitution in the inorganic materials. So therefore, one of the biggest motivation is to look up the substitution for the silicon-based electronic materials, electronic devices, so that we can have the less cost as well as your environment friendly things we can produce more. So this was a motivation, and objective was to design some p-type semiconductor, because these are suitable in terms of their stability for the device fabrication. So we have designed the two molecules. These are the two molecules which are basically showing the p-type your semiconducting nature. Let me come to the next slide. So this is the design molecules are the naphthalene, pyrol, and propanoic acid, and second molecule is naphthalene, pyrol, and pyridine. So this is based on the donor-π-acceptor model, which is widely useful in designing the sort of your dyes for the DSSC and for your mostly it is useful for the dye-based systems, where you want to have this electron puller and electron donor kind of arrangement, so that it can have the better passes of your charges to the semiconducting material, which we generally see in the DSSCs. Here we have come up with the idea that we can also utilize these materials for designing our p-type or your n-type, or we can also look up their ambipolar nature also. So our model is based on that, which is very versatile model for designing the novel compounds in the organic systems, organic semiconductors. So my methodology was to work on the density functional theory. Theoretically, we modeled these molecules, and we looked up their charge transport properties, and we did it at the hybrid functional and the polarized valence double zeta basis set we used for this calculations. And we also looked up the electric field dependence of these molecules and analyzed their effect on the homologue gap energy and the dipole. So here I can show you these are the optimized two geometries of my systems. This is your first is naphthalene, Pyrol and propanoic acid. So this part is your donor, and this is your spacer or the bridging element, and here you have this acceptor. Similarly, it is the second molecule which has a naphthalene, pyrrole, and this is your pyridine. So these are the optimized geometry of the designed molecules, and further we have looked up their charge transport properties. So let me just come to that. Okay, before that I'll go to the mechanism of organic field effect transistors. So we all know that transistors are the three-terminal device, and their semiconducting channel is basically it is a p-type or it is an n-type. It is sandwiched between the two of your electrodes, so it could have the npn channel or it could be a pnp channel. So there is a source, there is a gate, and there is a drain. So if we can if we have the voltage of the gate higher than this threshold voltage of this dielectric and this semiconducting channel, here you can see easily this is my semiconducting channel and this pink color is my dielectric. So if my gate voltage, or I could say that my source and the gate voltage, the voltage of gate and source is smaller, or if it is higher than this drain voltage, then I have this linear region of current, this drain current, and if I have this voltage VG equivalent to this drain voltage, then I first I reach up to the linear region of the current, and then I attain the saturation. That is called the pinch-off region. And similarly, you have, if the drain voltage is higher than this gate voltage, then you have a starting linear region, and then further you have the saturation. So basically this is the idea that if you can control this, if you change this gate voltage, so you can change the flow of you can control the flow of charges. So that's one of the important aspect of this field effect transistors, that we can control the flow of charges by the control of their voltage, your source and gate voltage basically. So what we've designed is, we have designed the semiconducting channel, and we have looked up their charge transport properties. Our result says that the charge transport properties are basically, we have done it through the calculation of reorganization energy of the electrons and holes, and this is basically the energy of the system which is changed, or you can say that the geometry which is changed from the geometry relaxation process. The energy associated with the neutral molecule, once I charge it, once I give a charge to this molecule, so what happens to the geometry after attaining a certain charge or after accepting the electron? So there is some changes in the neutral geometry. That change is actually comes from the addition of the charge or the release of the charge. So that's called the internal reorganization energy of the of the your electrons, or it could be your holes. So similarly, we have the external reorganization energy, that is your that comes from the polarization of the solvent molecules or the surrounding medium. So that how it affects our system, our molecules. So that concise the your external reorganization energy. So it's tough to calculate the external part, but it's easy to calculate this internal reorganization energy. So we have calculated that, and mostly researchers do that. So let me just results. These are my results, where if you focus on this whole reorganization energy, which is 1.08 into 10 raised by minus 5, and similarly electron reorganization energy is 1.9 into 10 raised by minus 5. So in both of the cases, in system first and system second, I have if I can, okay, so this whole reorganization energy is a smaller in comparison to the electron reorganization energy. Here it is, this my video I think this is hiding my values. This video title, this video tile is hiding my value. So in both of the cases, whole reorganization energy is smaller, and I'm running out of time also. It's 15 minutes what I wanted. So we have looked up the other electronic distribution in our picturization, and we have seen that as we apply the electric field, so the electronic redistribution happens from one end of the donor to the acceptor. You can see this from this side to the electronic distribution at 0 volt per angstrom, at 30 volt per angstrom, at 0.3 volt per angstrom. It moves to this side, the electronic distribution. So that's a good thing. That's a good thing in the sense that there is a transference of charges is happening in our system. Similarly, you see this LUMO picturization. Okay, so for the second system, the Pyrol pyridine based system, we have seen this HOMOs on the donor side, and similarly we have the whole LUMOs over the whole molecule, and there after, as we increase the electric field, that shifts towards the acceptor. So there is some shifting in the LUMO level, which is ultimately it is helpful in reducing the band gap. These are my values for the gap energy. So at 4.3 is at the gap of the molecule. This is your band gap of the molecule at 0 volt, comes from 0 electric field, and this increased electric field is 3.6. So it produces in the electric field. That's one of the significance that our electronic redistribution is happening in a much expected way of the molecules, and it is behaving nicely in the external electric field, which is also justifiable from the dipole moment. So you see that this is 2.6 to it increases to 3.6. That also justifies our electronic redistribution after the application of electric field. Similarly, it is happening in the second system. From 4.3 it goes to the 3.2, and dipole moment increases from 1.2 to 6.4. So in conclusion, I say that this lambda h values were very important to define the nature of the charge carriers. So holes reorganization energy is smaller as compared to the reorganization energy of the electrons. Therefore, we can say that holes will move faster as comparison to the electrons as the charge carriers, and this could utilize in the as a p-type channel for the organic field effect transistors, and it is also confirmed from our electronic distribution picturization of the charges through the HOMO and LUMO orbitals, and from the dipole moment calculations. So we hope that this is the one of the contribution in the field of organic electronics, or basically in the organic field effect transistors. So with this, I would conclude, and I would say thank you to allow us, or allow me, for taking part in this conference. Thank you for your time. Thanks.